Hey guys, welcome back to another stream. So this is day 58 now of intelligence maxing. So almost 2 months, which is pretty impressive. But today what I want to do is I have an assignment for one of my classes for school, and just want to do it right now. I think this one has to do with feature selection with lasso regression. And then also, so feature selection with lasso regression, and then also factor investing or creating factor models, maybe using some type of regularized regression as well. I haven't taken a look too deep into it, so I guess we can look at this together. All right. So I have on one end portion of my assignment you can't see, so download the data prob 1 CSV. All right. This is maybe title, import packages. Okay, I guess there's no way to do that. Let's see. So read in the data here. Read in quarterly data. So what I'm doing is I'm parsing the very first column in prob1.csv, and that is the date column. So I'm going to use the date column as the index, and then also turn that into a datetime object. So this here is a function that I defined in order to simulate a linear regression. So this is, I think, pretty straightforward with stats model. You can just import their API, and here's the setup. So setup regression problem. So I'm gonna shift 1 will move the column forward by 1, right? And then we just add a column of 1s. That's what add const does, so that the eventual matrix multiplication just becomes, I think, pretty simple. So this is the excess returns. So drop the first, because we are moving forward 1. Their first date is a, and then first date is nan, and the data set. Okay, so this is how we kind of run the regression here. Run regression. So we function to run OLS, run in sample OLS regression. Okay, yeah, it's pretty. So run regression for DP variable, and then run regression for XP variable. Okay, that's good. All right, create the training and test split. So we create the training period between 1871. Let's see. 1872 to 1926. And this one goes from 1926 to 2016. All right. Display. So I'm gonna add actually something here. I'll call this problem 2. Problem 1B. Yeah, okay. Display training data. It's curious to see this actually. So I'm gonna comment this out so we can just see here. So this goes from 1821 all the way until 1926, the very last day. Okay, yeah, I think this one works. Let's see. So I have to remember that this is always one behind, or all of these variables are kind of lagged one behind, right? And so if you want to predict from 1927, right. Include the 2016 values because TP, the regressors are lagged by 1. Include 1926 because the regressors are lagged by 1/4. Okay, that makes sense. All right. Okay, so that's good. So create model trained on training period, and then we'll do the same here. So okay. So we can see here, in the case of using the DP, we have a 0 R-squared. That means our regression is dog shit and very high p-values, so that is not good. We also have this where R-squared is also 0.04, so this is also pretty bad as well, actually. I wonder what it looks like if we plot the data. Maybe I'll worry about that after, but So out of sample r squared becomes okay, so this we want return results. Okay, so sample r squared, so dp out sample r squared, and then we'll do xp out sample r squared, and so we'll call this dp in sample r squared is equal to, we call this the dp model, and then we will do dots r squared. I think we could do the same thing, but we'll just use the xp model. Alright, so let's do print dp out sample r squared. Make this an f string. And then we'll do the dp out sample squared, and then dp out sample and sample r squared. And we'll just do xp, 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 and then xp. These are the exact same. Why is that? Okay, well, seems like out sample is actually better. The historical average excess stock return forecasts future excess returns out of sample better than the regression of excess returns on predicted variable. Note that a positive value for us is lower average mean squared error prediction than historical average. Right. Okay, so the question is asking us whether or not we think that, or whether or not using a predictor variable, in this case xp or dp, is better than just choosing the average being the average excess returns. And whenever we have an r squared that is greater than 0, that means our summa squared residuals for our regressor out of sample is actually greater than it's less than the summa squared residuals or the total summa squares whenever we're just using the average. So basically what this question is asking us, do we have a positive r squared or is it negative? Because negative r squared means that just choosing the average excess return over time is better than actually making a model. So in this case, we could see that there's two different predictor variables, dp and xp, and it seems like xp actually has a positive out of sample r squared, while dp has a negative out of sample r squared. So I believe that it's not consistent with the idea you have a... I don't think it's consistent with the idea that choosing the average every time is better, or is... yeah, I guess provides better results. Okay, I think what I'm going to do then is combine these two and then just voila. I think to delete this I do Command Backspace. Oh. Wait, Shift. How do I delete? Command Backspace, right? Oh, there we go. I have to escape from it. Okay, so that's good. And I'll create a little mark down here. Just say part B. So my results are not 100% consistent with Welch and Goyle. It seems maybe add a little emoji. Okay, so the out of sample R squared for the XP variable is greater than 0, though not by much, suggesting that XP. So it's around 0.1. I think it's 0.01, right? Yeah, 0.01. Although that is very low. Is a slightly better explainability. From the predictor variable compared to just choosing forecasting the average. Wait a minute. Oh, so we need total sum of squares. We do not need the ground truth, actually. We want the sample mean for not the prediction, but historical average, historical excess return, right? So we want this actually. All right. So we'll do mean historical training data. Okay, so training data, we will just take the so I think what we want to do is let's do mean historical average excess return. So this is going to be equal to training data, and then we will choose the RM minus training data RF, and then we will find the mean. So calculate the historical average excess return. Oh, wait. So it says up to date T. Well, I don't think we actually just use the training data itself. We want to calculate the mean historical excess returns up to the current dates. Oh man, okay, that's hard. That's hard. Okay, I have to think about this actually a little bit. Okay, sum of square residuals I think is fine.
It's like the last half too. It's like, is it? It is, right? I don't know. I swear to God it is. I thought she said that like last week, because next week's finals, right?
So this should actually be another vector as well, not a scalar. And this vector should include every single index, the mean historical excess returns of the previous periods before it. So how do we do that in Python? I don't exactly know. Is there like a rolling function to calculate that? I'm gonna ask ChatGPT to see if it knows. It's gotta be like a pandas function we could use to make it easier for us. I just don't know it off the top of my head. Alright. I have a list of numbers, a series, a pandas series. How do I make a new series? Whose value is all of the numbers, mean of all the numbers including and before its corresponding index. I feel like okay, so you take the cumulative sum. Okay, wait a minute. So let's think about this then. df, so excess return is equal to df to rm minus df rf, right? Maybe we'll do this. So df excess return going to maybe create a, so I'm gonna, how do I create a new cell again? Oh, fuck, then command enter, there we go. Okay, so df head. Alright, so excess return, that's good. We have a new column, and I think what we could do then is we take df and then we'll do, what's it called? Fuck, I'm blanking. Excess cumulative excess return. We'll do com excess return is equal to df return com sum Alright, so what is cumulative sum dot index? Shit, so there's a number there involved. Alright, fuck. What if my index is argdeets? Okay. It's actually pretty helpful, so we'll do quarters p dot a range. So we go from 1 to, let's see, length of EF plus 1. Right, and then we print quarters. Okay. think what we could do is we'll do divided by, so df average historical return divided by quarters. Then let's do df that head. Yeah, maybe not actually. So maybe we do want this from 0 all the way to 1. Let's see if we get the same thing. Okay, nice. I think this is what we could do. What I'm gonna do then is probably move all of this over here. Yeah, I think I'm gonna move all this pre-processing stuff over here. Let's see, so quarters. Number of quarters in dataset. Then creates create useful columns for regression later. Okay. So this is going to be excess returns, cumulative excess returns, simplified addition. So average excess returns dividing sum by the number of quarters. Okay, so that is going to be helpful. And now I think what we could do is, instead of doing the excess returns, we could just specify the column in our data frame. And I think that should work. Never mind. Oh, there's no S. Okay. All right. So let's delete this. Let's run this. I think we are getting the same, very close. Okay, yeah, we get the same answer as before. All right, now I think what we want to do is to the date t. Man, so this is kind of confusing with the time lag, but let's see if you can make sense of this. So we have our average historical excess return. So 1-to-1 corresponding. Okay, so let's actually take a look here again. TF.head. The one thing I'm a bit confused is we have, okay, so t plus 1, our axis return is, let's say this is t. This is t plus 1. When we try to use this to predict this, or I guess I should say this, we don't know the previous expected or axis return. So when we subtract by we shouldn't include this, so the average historical return right, if we shift this back, actually, if we shift this forward, right? So we have, let's say we shifted this forward one. Shift 1. Right, and this would be, this is t plus 1, so this is the cumulative axis return, and then this is the average historical return. So I think we would want to actually push this up by 1 as well. So dot shift 1. Let's see if this actually works. Maybe we could do -1. -1. Let's see if this works. Oops. Right, so we have this. Oh, shoot. Divided by quarters. Because then we have, this is the cumulative axis return before it at time t, and then this is the average historical return time t. Okay. I think then what we could do is the excess returns, and then we also have ground truth, and then the get this from average, what's it called? Average historical return. Okay, so we have the mean historical excess returns. Now you can just copy that, and we will, actually we could just add an S at the end. Okay. Oh, still getting error. Alright, what's the error here? Value is trying to be set. So what is this then? So what do you mean? Excess return. Okay, so I'm getting some warnings here. I'm not entirely sure what I should do. Let's try running this again. So we didn't have the problem here, right? Okay, nice. So now both of our in-sample R-squareds are higher. Okay, I am going to skip this for now because I feel like I've been kind of stuck on this for a while, and it's been about 20 minutes. I'll come back to it in a bit. Alright. So I think what we could do is change this to Markdown, and then I think this is probably going to be problem. So part C, and then Command Enter. So what is part C? Repeat the calculations of the previous part for F sample R squared statistics. Where A hat T plus 1 and beta T plus 1. Okay, so basically we have to say if, how do we impose the restriction? Because we have to say, look, we're gonna only use an alpha that's greater than 0 and a beta that's greater than 0. How do we do that though? Oh, I think maybe we can just do this in SciPy optimize, minimize. We can create a constraint, specifically the bounds of our function. Okay, so I'm gonna import SciPy dot optimize dot minimize. So SciPy dot optimize dot minimize. Right. So we could say results is equal to SciPy optimize minimize. What do we need to pass in though? I think we need to pass in the objective function. In this case, we'll call, so this is going to be our ordinary least squares objective function, and then really all we need to do is we need to return the sum of square residuals of our, so we have ground truth minus our prediction, and then we just square it. Okay. So ground truth, prediction. Right, do we want to put a negative here? I don't think so, because that would maximize it, I think. Yeah. Okay, so we have our OLS objective function, and then let's put in our sorry. I'm not entirely sure if this is exactly what we should do yet, so I don't think we should just do data actually. So we want our data, so data, and then coefficients. Okay, yeah. So we actually want our coefficients to be first, because this is what we're trying to optimize. Okay, so let's try to get the dimensions here right. So coefficients is a, then ground truth, and then data. So the dimensions of the ground truth and the coefficients should be the same. We'll call this n by 1, and then no, they should not be actually. So data should be n by m, and then we want our coefficients to be m by 1. All right. And so m is equal to number of dimensions. So these are regressors, and then n is equal to number of observations. Yeah, that makes more sense. Okay, so that being said, what do we want to do here? I think we want to do our data, and then we just do the matrix multiplication with our coefficients. Okay, so training data, let's see here. So training data dot shape. Two, two, one. So in this case, well, there will be two. So one predictor, one constant. I think that makes more sense, right? Because in this case, we're running a kind of univariate or single variable regression. We really only want to predict or use one predictor and then one constant. So I think the dimension of our data is going to be just n by 2. All right. So we have that, and I think we can just try to test this out, see what happens. So let's try. Okay, so we have our objective function defined here. We want to minimize this, and guess x0, we'll just guess 0.5. So our first initial guess is going to be 1/2, and then pass in some arguments. Okay, so arguments, we want to pass in for the ground truth, training data, we'll put in the excess returns, and then actually, let me see this. So ground truth is equal to training data, excess returns, and then data is equal to not training data, should be testing data. And then I guess we could do XP first. See what happens. So I think this is something with the dividend yield, the smooth dividend yield, whatever that means. Sum dot add constant, and then we'll add a constant to data. Okay, so now we have our two variables, and we can just pass them in here to the args parameter. So data. Okay, and then I think last thing, actually let's just see what happens here. I don't even want to worry about the bounds yet. Alright, so we do have an error. Must return a scalar value. Oh shoot. Alright, we want the sum of this. np.sum. Ideally, we should be getting the same thing in terms of our coefficients here. What was our coefficients for XP again? Right here. Oh wait, no, sorry. I think we were right actually with using the trainer data, because we want to train first on the training data, and then let's see here. So XP is negative 0.0141 for the constant. Shit. What does data look like? Display data. Alright, yeah, let me run regression on the XP. Oh, wait. that is on the entire data set, I just realized. Okay. What if we run the regression on the training data set too? Run regression XP on training data. So we have the same problem, it seems like, 0.02. What if we just did negative for the sake of it? Yeah, I don't think so. Yeah, I'm kind of at a loss here because our coefficients just aren't matching from our OLS regression. And I feel like we're using the exact same data here. Right, so for our OLS objective function, we're just taking our ground truth sort of label, and then we're do we have to shift this by 1 actually? Okay, so I think that was the error. I forgot to shift the returns up 1 because they're always lagged. Fuck, alright. This thing is always so confusing because of that 1 lag date. But this is good because they both match up in terms of the coefficients when we both use optimize, minimize, and also when we just use the stats model API function. Okay. So I think the last thing we need to do is just set the bounds, and I forgot how to write this, like the syntax for it. But basically we want to force both the coefficients, the constant, and the smooth dividend yield to be greater than 0. I'm gonna just see what ChatGPT says. I force coefficients to be 0. Okay, I guess it's as simple as just doing this. Just creating a list of tuples. Tuples of none, 0, none. Norm of projected gradient. Uh-oh, what does that mean? I honestly have no idea. Let's see. Okay, so I'm going to maybe add a little markdown here just to kind of explain. ChatGPT says this means the algorithm decided to stop because it was close enough. It's close enough to 0. Okay, I think that's what it means, so that's good. All right. Maybe you might want to make a function for this to make it easier. Not entirely sure though what I should do for it, so let's call this def. Run restricted regression. I guess that's a good way to mean so variable, and then data. So change this to data. Ooh, actually, yeah, that's not good. What did I name this? Call this df. Okay, I'm gonna delete this too. Let's return the results. Call this a function, so function to run the restricted regression that limits ensures all coefficients are greater and or equal to 0. Okay, that's good. Let's evaluate on excess terms, so still need to shift by 1 here. So add a constant for the alpha coefficient. Okay. So bounds here helps limit the coefficients. Greater and or equal to 0. Okay, that's good. So I'm gonna say we have part C done, at least a very simple version of part C. Now we can just move on to question 2. And this is talking about the ridge and constrained optimization stuff. All right, I'm going to change this to Markdown. So let's call this problem 2. This is ridge and constrained optimization. All right. Probably gonna use the bathroom real quick, actually. Nice. Gonna think about this. Okay, gonna come back real quick. Oh shoot, I gotta charge my computer too before it dies. Yeah, I'll be back. guys, I am officially back from the dead. I'm gonna try to pull out my monitor again. Okay, let's see what we're going. Oh, nice. So everything loads. Alright, we're doing pretty good here. So, ridge and constraint optimizations. I'm going to read through the question here. 3x2, sir. So note denotation, I guess the norm of x, the L2 norm of x squared is equal to x transpose x, which is equal to the sum of x. Show that beta L plot level sets of the objective, i.e. contours of beta which satisfy x beta minus y squared is equal to c. Okay. Okay, so it seems like the questions here are both mathematical and also involves a bit of coding. The first one kind of has to do with the theoretical concepts of ordinary least squares, and then the second question goes a bit deeper to extending the problem towards regularized regressions like ridge regression. Okay, so I think let's start with problem 1 then. So parts, let's see. Part 1, so show that you have the beta hats. Beta hats of OS is equal to, so we have x transpose x, the inverse of x transpose y. Okay. start. Okay, maybe to start, the main objective is the way we find, say,
Where did Shannon go? Just disappeared.
just okay. To start, we can to start. It's helpful to note that beta. Let's do slash at beta OS can also be defined as the following. Alright. So this is also equal to, we find the, I think arg min, is that something? Yeah, alright. Arg min of beta of I think left, and then right. Oops. Okay, so we have x beta, oh sorry, y minus x times beta. And then we have okay, so arg min just means to minimize this function by choosing the, just means to choose a set of betas that minimizes the function. So arg function by change just means to find the right betas that minimizes the function. Okay. Okay. So with that being said, okay, so I think this is the L2 norm squared, right? So the L2 norm can be defined as we take the whatever's in here, so this is like an element, and then we square that, we add all of these sums of the squares, and then we take the square root. So this just becomes argument beta of y minus x times beta, and I think we square it. So let's try to write this out. Maybe and beta y minus x beta. Right? And then we just multiply this by twice. That's right. Yeah, I think using these would probably be better. Little square brackets, although I can't seem to find it. There you go. Alright, if we multiply this out, this becomes, I believe, okay, so this becomes, I believe, we take y squared, right? And then we multiply, so y minus y x beta minus, okay, I think it's 2 times y x beta, and then we add x beta squared. Yeah. Okay, so now we have 3 different kind of terms here in this polynomial, and I think what we could do is, so I'm not entirely sure how the exponents work with a matrix and a vector. So yeah, this ends up becoming a vector, right? And then we just square that vector. Is it the same as squaring this and then squaring that? And then multiplying the 2. Also, this is a n by yeah, I think this is more helpful. And let's see, the dimensions are also full to note to write down the dimensions. So we have for me to write down the dimensions. Okay, so we have y is equal to n by 1, and then x is equal to n by m, and then beta is equal to n by m by 1, way, and then we there have, so beta x is equal to n by 1. Oh, sorry, it's x beta. Yeah, x beta is equal to n by 1. All right. So then I feel like at this point we probably want to take the gradient or the derivative. Yeah, the derivative here, because we have a single matrix, single vector beta. So we want to take the derivative of this function, set this equal to 0 to find the betas that'll help minimize this function. I think then, so this point comes. Okay, so I have to say that I'm not super comfortable with doing all this matrix vector calculus stuff. It's been a while since I've learned about it, and also I don't really remember it that well, and I didn't even understand it in the first place. But in this case, maybe we could kind of break this down into steps and use ChatGPT to kind of fill in the knowledge gaps. So we need to take the derivative of this function with respect to beta. Beta here is going to be a vector of n by 1. So this term, I think, automatically just goes to 0. We don't need it. This term maybe becomes 2yx. And then the beta disappears. And then this becomes So first of all, can we even do this matrix or this vector multiplication? Because this is n by 1, right? And this right here is n by 1. So how do we multiply the two vectors? We would need to transpose one of them in order to get the dimensionalities right. So what is the dimension of this, right? I feel like this is kind of undefined here. If we want to add up all of these, or I guess subtract and then add, they all need to be n by 1. And so maybe we could transpose this. So this becomes x 2y times x beta transpose. Plus x beta squared. Alright, let's see. So we have beta two times beta. Oh, wait. So y becomes 0. Yeah, I'm kind of lost here, I'm not gonna lie. Yeah, let's see. Oh, so there is a transpose here involved. How do you... How can I interpret the square of a matrix? So what? Guess you also have so this is where it gets a bit confusing, but going to try to make sense of what this is saying. So it seems like there's one thing that I'm missing here, and it's one more helpful definition So turns out that so left x 2 2 slash right is the same as transpose x. Okay, here we go. Yeah, there we go. So when we say that, okay, so when we do this, then this is the same thing as taking this transpose times this. And so this becomes a n by 1 by n. This becomes n by oh, right. So this then becomes just a scalar. Okay. So that means this function is wrong. How do we think about this? So we have how do I distribute this transpose? Say this. Okay. Some more notes about transposes, matrix factorations. Okay, this is actually going to be helpful. So you could do so A plus B transpose is equal to A transpose plus B transpose. Same with minus. Okay. Subtraction. Okay, and then we also have, so I think AB is equal to AB transpose is equal to B transpose A transpose. Right, there we go. Oh shit. So let's say this is 4 by 1. Okay. So with that, we could maybe redefine this statement as, so it would be y transpose minus beta transpose, then x transpose. Oh, shoot. We still want to multiply this by y minus beta. Right, and then if we multiply this, so y transpose y, this will be a 1 by n by 1, so this will just be a scalar. So it'll be y transpose y, and then y transpose x beta, so this is n by 1, y transpose will be 1 by n, so that works. Beta transpose x transpose. So beta transpose x transpose, this will be 1 by m and m by 1. So this will be 1 by n. And 1 by n times n by 1, that works. 1 by n times n by 1, that also works. Okay, so the dimensions now match up. That makes sense. Wait, okay, so we have y transpose y, and then we have beta transpose y, right? I think we have 2 of those, so we have minus 2 times beta transpose, right? And then we will add beta transpose times x beta. Right, so I think we get here, and there's really not much more further simplification we can do, I don't think. This just becomes 0, beta transpose. See, this is where I'm kind of confused, because how do you take a derivative of a vector value function with respect to a vector? How do I take the derivative of a vector value function? So vector value function is just a function that spits out a vector. Oh, the Jacobian matrix, fuck. I totally forgot about that. It's just a matrix of partial derivatives, I think. So at this point, the function to inside the argmin is kind of scary, but so I'm going to take a second to break down the dimensions. Alright, we have y transpose y is equal to y1. Oops. So we have 1 times n times n1, which is equal to 1 by 1. Alright, nice. That actually makes this a lot more clear. Okay. Minus 2 beta. So beta transpose x transpose y. So beta transpose is 1 by m, n by n, and then y is just n by 1, which is equal to 1 by m, 1 by 1. Nice. There seems to be a common theme here. So 1 times m, m times n. Right. And then we have beta times n by m. And then last one is n m by 1, which is equal to 1 times 1. Oh shoot. Here we go. Everything at this point simplifies down to a scalar. So this point, so scalar is the sum of squared residuals that we are trying to minimize. Okay. Okay, so that's good. Let's use scary. the little emojis. Alright, so once we have this, I might want to do I. Yes, sir. Oh, I see. Okay, but there's two things here that I have to think about. So the derivative of can you explain the second, third derivatives here and how the rules of a term beta transpose B where beta is oh shoot. Derivative of is the derivative. So the gradient vector. So if we derive the gradients, gradient with respect to beta becomes a bit easier. Breaking it down into 3 different pieces. Okay, so if we break it down to 3 different pieces, right? So we have the gradients. What does the notation guess we can do nabla. So nabla with respect to beta. Zero. Okay, so that's good. Maybe for 2 with respect to beta of which is just equal to 2x transpose, oops, ty, and then I believe this is beta, okay. So this is the quadratic form, right? I think this was beta 2 times beta x transpose x. Beta yeah, I'm not entirely sure how the quadratic form. What is the intuition behind transpose x? Derivative. Okay, so I'm trying to read this little, there's this little blog post. I'm hoping it can lead to some insights, but I'm still so confused on how you take the derivative of a quadratic form. I guess this is what a quadratic form means. So you have x transpose ax, or ax is some type of, A is some type of matrix, x transpose x, x is a vector. I guess this leads to a scalar function. So intuitively, it represents the rate of change for f at the point x, in particular starting at x. If you move a distance of h, I want to figure out how much f change you'll multiply to. And add it to f. Sorry, so fx plus h is approximately equal to fx plus f prime x times h. Note that the last expression, so gamma h is equal to f prime is. So x is closely equal to f of x plus f prime. We use the same notation for the generalized derivatives as we do for the usual derivatives. It shouldn't matter. The usual derivative is a special case. So think of f prime x. Okay. Okay, wait, let me think about this because point x is a vector. I'll claim without proof that this works. Or of course h is a vector as well. So this is a matrix of partial derivatives. Since the result of x is an n vector, we can think of f as working component-wise. F of x is equal to f at case. Wait, so this is a collection of functions. I'm not entirely sure what that means. I guess we'll see down here. Excuse me. Okay, so I think this is actually pretty important because this is the dimensionality that our OLS objective function is trying to go to. We're trying to go from Rm, so any arbitrary high dimension, to just the real numbers. So that's our sum square residuals. That means our Jacobian matrix is just one row. Since there's only one component function of f, we drop the subscript on f1. So the transpose of the row j f x, usually called the gradient of f at x. So the derivative of this function with respect to x is just simply b transpose itself. Okay. Of the same derivative, b transpose. Oh, wow. Okay. Ax plus ah. Yeah. Okay, so f of x is equal to x, so f just equals a. I guess we can distribute a matrix. So x plus y is so how f with respect to y and y with respect to x? Interesting. Oh, so y is a function of x. Okay. So it's equal to x transpose. Alright, I definitely need to save this. Some of this is clicking, some of this is not, so I'm going to create a flashcard real quick and try to make sure I do not forget about this. But yeah, this is OP. Alright. Multivariate linear regression. I'm going to create, we'll call this matrix vector calc. Okay, so what should I just start off with? Let's say, what is the derivative of beta transpose x?
They call them deliberations, but it's basically they're leading a discussion activity.
Okay, so just gonna start that. Simple flashcard. Let's see something real quick.
My understanding is that they're persons that will satisfy the capstone requirement, and whenever you take that course, you work on whatever your capstone is, and you present it here and now. So if you took it in the fall, you just have a little bit of a gap. How do you guys do it?
So during this semester, how are you? We prepare.
Allison, if you're watching this stream, I want to see you. I want to see you. Okay, so that's good. Combining everything together. Okay, so the gradients of is equal to 0 plus 2x transpose y plus 2x. Should we? I think this is minus, right? Yeah, it's this. This is minus. So minus 2x transpose x beta. Combining everything together and then setting the gradient to 0. So it's times the minimum value. Which is equal to 0. Then we have 2x transpose x beta is equal to nabla. Okay, and then the last thing we could do is take beta. Okay, wait, so this becomes n by n, right? Wait, n by m, and then this is x transpose will be m by n. Yeah, that's good. M by 1. So it'll be m by 1 times m by m1. There we go. Let's go. All right. So we do have this done. Okay, there's a lot of math, but that's okay. So we have that. And then now we have to plot the level sets of the objective. So for, let's see, C in range. So let's do 0, maybe 5.
And then go into the Zoom panel, and then I can do the Zoom panel, or you can do something. And then For the key takeaways, I don't know. If I mean, like I can do it, or also like some people do it. Whichever one. Or you can do it if you want to. But, oh, was yours? Yeah. Yeah, it's my only view is it's like read off the slide.
Okay, so let's actually define x. So x is equal to mp dot array.
I'm gonna push one of those out. Because you're making that one.
We have 1, 1. Oh, wait. Right, and then we have 2, 3. And then 1, 2. So y is equal to 1, 2, 5, 1. Alright. So print x dot shape, print y dot shape. Oops, mp dot array. Okay, 3 by 1. That is good. And then the vectors. So beta is equal to. Okay, so we have two vectors, right? And then we want to multiply. Yeah, I wonder how you can do that in Python, like finding the functions or the values of beta that can solve it. Copy this.
So that's why I was like, do it. I'm not going. I won't talk. And I was trying to get SciPy optimize.
minimize. What is root finding? Not entirely sure. Okay. Yeah, so it seems like this one is a bit more complex than I thought it would be. I'm not entirely sure if we can use SciPy optimize, minimize, because we want to find all b's, not just the b that minimizes this function. So maybe we could just possible beta 1 values is equal to mp.array. Just make a shit ton of these. And we'll do negative 100 to 100. A range. Right, so we have possible beta 2 values. I guess, yeah, that's fine. C is equal to array 0, 1, 2, 1, 2, 3. Okay. What does a contour plot look like? Okay. Wait, what is mp.meshgrid? Oh, wait. So they do this actually, which is interesting. So what does beta 1 look like? Dots size maybe? So I guess this flattens it. Dot size. Okay, so it's the same. What does Ravel do? Doesn't do anything with the size though.
No, I don't think so. I believe that's just like the first. That's why they were really good. Because they show like here. Okay, so I have
Oh, okay, okay.
or how it's supposed to size up. I was saying that Eric should do the like introduction of it and then go into how it's not a panelist.
In my backpack.
Slide. You start the organization slide and then you do the goes. And
Okay.
he does,
Yeah, I might come back to this question. It's a bit difficult.
And then I do the Zoom panel, like the Zoom panel ones. And then maybe you end it with details. How you can so we go into balancing? Yeah. Or like she would start, you would end. I just feel like that's the best way to break it up because it's 10 slides. It's kind of weird dividing by 3. Yeah. But I don't really count the like first and the last.
Okay. Yeah, I'm gonna come back to this. So this one's a bit hard. I'm gonna go to maybe problem 3. And my eyes are starting to hurt, so honestly, I think I might end the stream soon. Oh, skip this version. Yeah, we've been doing this for about almost 3 hours now, so I need to give my eyes a break. All right. Let's see. So problem 3. Let's do df is equal to pd dot read csv. Shift E. Nice. Okay. Regime 1. U.S. equities. Okay, so factors is equal to world equities,
We've gone too far.
U.S. Treasuries, bond risk premium, inflation protection, currency protection. Okay, so let's do date parser, date, and then we'll do use index calls. Okay, I'm gonna close this real quick. I think my computer's trying to slow down a little bit, but let's use the date column as our index. I think maybe we should do this. List object is not callable. Oops, okay, I'm getting a call real quick. Hello? Hey. Okay. Yeah. Wait, where do you need to go for that? wherever it is, I think you'll be able to make it. Yeah, regions? Okay. Yeah. Okay. I can also meet you at Francis Scott Key later. Oh, I'll just meet you there and I'll walk back with you to Regents. Yeah. Can you maybe... Actually, you don't have to call me when you're driving, but whenever you get to... What's it called? Whenever you park, just let me know. Yeah. And then I'm at ESJ right now. So I think maybe I could meet you when you park. Yeah. I'd like to see where that is, because I'm not entirely sure. But I feel like you would have to cross through ESJ regardless. Or in that direction. So maybe I'll run into you. Alright, well, drive safe though, and I'll see you soon. Yeah. Sir. Okay, I'll see you. Alright, let's try to bada bing bada boom this and get the hell out of here. Display df. Okay, so we have factors, and then let's index by the factors, and then we'll do factors is equal to, and then we'll display df factors. Oh no, US Treasuries is not an index. You guys spelled something wrong. Let's see. Display df US Treasuries. Okay, yeah, I spelled that wrong. Okay, so we have a list of treasuries. That's good. Sorry, not a list of treasuries, but a list of factors. And then we want to first, let's create an artificial noise variable, right? I think we might want to import, actually, maybe we could do numpy random. So mp dot rand, so rand n, that to create array of randomly generated numbers are distributed normally. Okay. So we need to create actually first, world equities std is equal to df factors world equities dot standard deviation. Number of samples is equal to df factors equities. So we have length. Okay. So mp.random.normal. So we have is equal to 0, and then scale is equal to world equity standard deviation, number size to number of samples. Here we go. Generates noise with mean 0 CD of world equities. Okay. And then I think after we do this, let's add this to our DF factors. We'll call this noise is equal to DF factors world equities plus noise value is trying to set a copy of a slice from a data frame. Okay. Dot lock world equities. So we want all the rows. Wait. Can we do that? Okay, so maybe what we want to do is say noise is equal to DF factors, and then we'll do US equities. Actually, I think it's world equities, right? World equities plus noise. Fuck. It's the same thing. Yeah, I have to see what the problem is here. But I'll just save that for now. Getting error here. No warning here. So why is running an OLS regression problematic? I think the OLS regression is problematic because we have some multi-collinearity going on. So the world equity seems to be somewhat correlated, or noise is correlated with the world equities. So let's do right, we'll do x is equal to x is equal to, we'll call this DF factors. Y is equal to DF real estate. And then we'll do SM dot OLS. So model YX, and then results is equal to model dot fit. Oops. print results that summary. So this is problem 3. Problem 2. So part 2. Problems might arise here because noise is very similar to the world equities term. So go deeper later. Yes, so I need to probably go a bit deeper than that, but high level, that's what happens. Okay. So if you use scikit-learn, run lasso regression on real estate. Yeah, I'm going to take a look at how you can use scikit-learn. Scikit-learn lasso. So lasso regression is the L1 norm regularizer, and I believe here the really main goal of using lasso is to do feature selection, so that'll give us hopefully the features that matter here in order to determine returns for real estate. Okay, so it seems like this is what we can do, and then CLF is equal to linear model dot lasso, and alpha is equal to, so in this case it asks for 0.1 and 0.001. Okay. Okay, so then we can just pass in the same thing, it seems like. So results is equal to CLF dot fit. Then let's pass in, so this takes X and then Y. Alright, so print results dot coefficients maybe? So it seems like the only thing that really matters here is world equities. And then when alpha is equal to 1, alright, there's definitely something wrong here. So if we decrease this, the penalty becomes less. If we increase this, the penalty becomes even higher. I have a hard time believing that maybe it's different, so right. There's also the idea of an intercept, so wait, also CLF dot coefficients? Same thing, okay. Dot intercept. Okay, it's interesting. The response from regressors on measuring returns you do not have to standardize. So what if we did a alpha of 1? Yeah, it's still nothing. About 0.01. Nothing. 0.001? Okay, well, it's weird, because if we increase this, then this actually increases. I would assume that it doesn't happen like that. But at some point, our alpha just becomes really high, and we just lose everything. So this is from part 3. And part 4. Elastic net regression. Okay, so elastic net scikit-learn. So what if we do 50%? Okay. Random state. What does random state do? Okay, so in this case, let's do pressure is equal to scikit-learn linear model dots elastic net. So alpha is equal to, let's say, 0.01, and then actually believe if we set the L1 ratio, I set this equal to 1, this should be the exact same as before. So regression dot fit xy and print regression dot coefficient. So same thing. All right. 0.5. All right, so we're getting okay. So this is our elastic net. I'll take it as it is, and tenfold cross validation. I1 ratio is the measure is row and slides. 1 is equal to ridge. Lasso. 0 is equal to ridge. All right. Scikit-learn lasso cross validation. Okay, so there's something called lasso EV.
I was kind of wondering that too, actually.
Okay, so it seems like you can, there's this built-in cross-validation function within scikit-learn that can do everything for us, which is nice. Problem 5. Linear model dot lasso CV. And then we do cross-validation. So this is the number of folds, and okay. Reg.fits. I think we have XY. Let's just see if this works. Reg. Dot. What is a random state is equal to 0? Okay. Reg dot fits, reg dot score xy. What's this do? Dot get params. Okay, so probably gonna end this here, but I think this last one, I just have to kind of fit this lasso regression using cross-fold validation. 10-fold cross-validation. My mind is starting to shut down a little bit, so I need to go outside and get some fresh air. God damn. But thanks for tuning in. I think we made a lot of progress today, actually. Skipped through a few of the problems that I didn't really know how to do. Learned some basics of matrix vector calculus. I think this is pretty important for me to hopefully build upon in the future, but was able to kind of prove mathematically how beta OLS is equal to argmin of y minus x beta. So this is the L2 norm of this vector. And so we're trying to minimize this L2 norm based on changing the beta, in this case, this beta right here. And then our estimator is the beta that does minimize the L2 norm. Okay, so with that being said, thanks for tuning in, and hopefully I'll do another stream today. If not, then see you guys tomorrow.